Hey everyone. Let's just get started straight into the leak code because there's a lot I have to do. Um, Probably explain everything later, but yeah. Um, so I did this problem previously when I was preparing for Amazon, but I can't lie, like I just it's been a while and yeah. So I'm just gonna start off saving the dimensions in M and N. So M equals length of grid and grid 0. So obviously we're going to use DFS or BFS here. Mark, as soon as we inquire one that we haven't seen before, then we're going to traverse through as far as we can, mark them all as seen, and then increment the number of islands. So let's just instantiate result. How do I want to approach this scene? Usually, I remember reading somewhere you usually use a hash map. Let's just do a hash map. Equals this, and then every time we see something, we'll add it to the hash map. How do we write DFS? I guess we can just iterate through every element and run it if it's not in the hash map. So for R and M and for N, C and N, if let's just use can we use a set, like scene equals set? If RC in scene, then continue. Else scene dot add RC. How do we run DFS? Bro, this is what I'm saying. Like, I really need to lock in practice and maintain a consistency, which is what I plan to do. This is low key, like, So I added it to the scene set. How do we traverse through DFS? So we need to call it on the neighbors, obviously. How do we make sure it's in bounds? So right now I'm just currently figuring out how we can traverse. Do I write like a helper method? I think I'm gonna do that while we run DFS. Um, so then we'll mark if this low-key goes in this function. So yeah, so basically, right. Because we need to check this for every single time. So if it's unseen, then we continue. I guess it wouldn't be a continue. Break. So the hardest part is just like implementing the code, thoughts to code. Like I literally know we need to run DFS, and literally as soon as we finish DFS, like as soon as we hit water, then we'll increment count. We just run through and call it DFS. It's just now I just don't know how to implement it. If R CNC and then we break. Then we'll add RC to scene. How do we check if it's in bounds though? Or like some shit like this, but it's gonna be out of bounds. Shit. Oh fuck. I mean, shit. Because if we bump into, then we'll just return. Oh, I'm low-key just. I'm gonna watch the video, and I know it's something like this. I just don't really know how to, like, I need a review how to use adjacency lists and adjacency matrices and how to perform DFS and BFS and all that stuff. I don't know. I should know how to do this, so. Pause my music.
Let's solve
Why the
LeetCode.
fuck does YouTube look so big? What?
LeetCode 200, number of islands. This is actually one of my favorite problems because I feel like a lot of graph problems build upon this one, and you can learn a lot from just this one problem. It's also a really popular interview question. A lot of big tech companies, including Google and Uber, ask it, so it's a good question, a common question to understand. So we're given a 2D grid where ones represent land, zeros represent water. We want to count the total number of islands that exist, right? And in this case, an island is defined as ones being connected adjacently, horizontally, or vertically, not diagonally, right? So they have to be connected horizontally or vertically. And the entire grid is surrounded by water. So in this example case, we can see that there's only one island, right? This portion of ones, and they're all connected horizontally and vertically, and there's nothing else. The rest of the grid is just made up of water, so we don't have to look at it. So if you don't know how to solve the problem, the first thing you should do is not try to write any code. Just look at the picture and try to get as much information as you can. So think about it. How would a kid solve this problem if you gave them the picture and told them to count the number to this one? Numbers of this one above it. Well, it's already visited, so we don't want to mark it visited either. This, and the fourth layer, we had just a single value. So this is really easy to visualize, and if you already know this algorithm, you can code it up pretty quickly. So knowing what we just learned, let's code it up. So the first thing, just do some input validation. If we had an empty grid, we don't want to have to run our algorithm, and we can simply just return 0. There aren't any islands in that case. The next thing I like to do is just get the dimensions of the grid, so the number of rows and the number of columns. We can get the number of rows by doing this, and the number of columns by doing this. We also want to be able to mark positions or cells visited when we're marking island masses. So I'm going to use a set to do that. We could also use a 2D grid if we wanted to, but I think sets are a little easier. We also want to count the number of islands. We can initialize that as 0. So we want to visit every single position in the grid. So let's iterate through each row and column. So R is going to go through every single row. C is going to go through every single column.
Bro, I literally have like similar start for sure, but I feel like
if we visit a 0, we don't have to do anything, right? But if we visit a 1, then we have to do something. Then we have to traverse it and mark it visited. And don't forget that this 2D grid is
actually even checking that. I don't think
actually made up of position in the grid. So let's iterate every single visit of 1. Then we have to do something. Then we have to traverse it and mark it visited. And don't forget that this 2D grid is actually made up of strings, not numbers. That always trips me up. I think it's kind of annoying that LeetCode does that, but it does. So now we have to run our traversal. I'm going to run breadth first search because I kind of like it. So run breadth first search on this cell, row, column. We also have to increment the number of islands. But remember, we're only going to be incrementing the number of islands if we get to a one that we haven't already visited. So we're going to make sure that if we execute this, we've gotten to a position we haven't visited. And then ultimately, we're just going to return the number of islands. But we didn't actually write our breadth first search. Let's do that right now. So breadth first search is not a recursive algorithm, it's iterative. So we need a data structure to use for memory. So a queue is normally used for.
Wait.
So breadth first search is not a recursive algorithm, it's iterative. So we need a
So is DFS okay? DFS is recursive, right? Let's do.
we need a data structure to use for memory, so a queue is normally used for breadth first search. So we want to mark this position visited as well. So to visit, we're going to add this cell that we're about to. First search is not a recursive algorithm, it's iterative. So we need a data structure to use for memory. So a queue is normally used for breadth first search. So we want to mark this position visited as well. So to visit, we're going to add this cell that we're about to use our traversal on, RC. We're also going to add it to our queue.
Okay, and then while it's not empty, you run on the neighbors.
And so while our queue is not empty, that means we're going to be expanding our island. So we're going to pop from the queue. And we want to check the adjacent positions of this position that we just popped. So the way I like to do that is use a loop. So we know that there's 4 directions that we can go in. The direction to the right, which is 1, 0. The direction to the left, which is -1, 0. The direction above, 0, 1. And the direction below. Now, for each of these directions, we're going to check something. First, we want to check that this position is in bounds. The way in Python I like to check that is just if r plus dr is in range of rows.
What the hell? This is weird.
And check that.
Does he always do PFS like?
Use a loop. So we know that there's 4 directions that we can go in. The direction to the right, which is 1, 0. The direction to the left, which is -1, 0. For each of these directions, we're going to check something. First, we want to check that this position is in bounds. The way in Python I like to check that is just if r plus dr is in range of rows. And check that the column plus direction that we're moving in is also in range of columns. And that this position is a land position, so...
And it hasn't been visited.
This is equal to 1, meaning it's land. And lastly, that this position hasn't already been visited. So if this is true, then we can...
I guess this is smart. Because I mean, I was trying to figure out what's an efficient way to check that it's also in bounds. Definitely this.
Add that to our queue because that means we have to run breadth first search on this cell as well. We also have to mark it visited so we don't visit it twice. I noticed that we're doing this computation a lot by adding row plus different direction of row, so I'm going to fix that really quickly. So that's a little bit cleaner. And that's pretty much the entire breadth first search function. It's going to be running until the queue is empty, which means that there's no more land positions to visit. I had a queue is empty to use visit until the queue is empty, which means that there's no more land positions to visit. I had a sloppy bug. I forgot to add this row column position as a tuple, which we want to do as a pair. We have to use visit add, not append, because it's a set, not a list. And we have to pair, not two elements separately. I also used the wrong on a list. A few of the bugs that I had, I hope that they didn't trip you up too much. And also,
Oh, Loki, I forgot there's a editorial. See how they code out DFS. Bro. Okay, they call it DFS on the current. The current. See, this is annoying. Why would we set it equal to 0? That's kind of dumb. Oh, because I guess they're not marking it as visited. I'm doing it like that. Wait, I feel like I wasn't too far. See if I can build off all of this. So if it's already seen or. So if it's seen or zero, so if it's a 1, then we run DFS on it. After we can increment by 1. So if RC and scene or grid RC equals 0. So if it's already seen, if it's 0 or no. No. Let's do this check first. Oh. Even if the cell was already visited as part of it. Okay, wait. Yeah, I was thinking about that. So if it's a 1, then we'll call it. Oh, I see. Great. All right. It wasn't too bad. I was actually pretty close, like way closer than I thought. Some silly issues. Um, Considering I haven't done this since February, I would say not bad. I honestly also really like this problem, but let's just make notes so that we can easily go back to it. These are not valid, so obviously if it's out of bounds, if it's been seen, um, or if it's a zero. Then obviously we don't want to call on this. We add it, recurse, and then for every single one, it's okay if valid. So valid condition is if it's a 1 and it's not been seen. Then we're going to run DFS and increment it by 1. Sorry, I'm actually on duty as an RA today, so might get a few calls. Yeah, I mean, it's pretty simple looking back. I did a problem Candy Crush, and one of the other things was that like I didn't really know what to do with out of bounds, and now that I think about it, like for this problem it's really simple. You can just check if it's whatever, right? But for that one, you just loop. You just loop like on the first index and then one second to last element. Okay, wait, this isn't bad at all. If it's not valid, then we're going to return it and then recurse otherwise. And then, yeah, for each one, if it's valid, so it hasn't been seen as a 1, it's an island, then we'll run it. Okay. Let's read this little thing on adjacency list versus matrix. Okay, so this is how to represent a graph. Let's just look at the visual thing. So 0, 1, 2, 3, 4. So 0 and 1 should be an edge. 1 and 0, there's an edge. 2, 1, there's an edge. So 1, 2 should be an edge. Oh, so it's like diagonal. Adjacency list. array of linked list. Index of the array represents a vertex in each element. Just okay, that form an edge. So like maybe like a hash map adjacency list. 0, 1, 4, 0, 2. So I guess we could say it uses we can use like a hash map instead, where the key is the node and the value is a list of neighbors. So for example, 0 has 1 and 4, 1 has 0, 2. Okay. I've never used a adjacency matrix for DFS, so hopefully I don't get asked that in my upcoming interview. Monotonic queue. I don't know why I had this, but LeetCode used a deck for that, right? Like for... Hold up. I do want to just glance at this code again.
Regular pop.
Oh shit, I didn't... I forgot to return. Like this is good practice for interviews, but like if not created, then we're gonna return. Yeah. I remember one thing on LeetCode, it was like the temperature problem was a monotonic something. You know, stack, monotonic stack. Daily temperatures, yeah. See, I haven't even finished this list, and honestly, I'm gonna repeat it. Like I'm low-key gonna start over. This time, I've already, if you watched before, I've already done it twice. If I go quick, I should be able to if I like if I actually do know it, it should go by quick, even if I'm redoing it. And I'm gonna take this to prepare very hard. Very, very hard for interviews. Especially next recruiting cycle, because it's already September and I mean my LeetCode definitely isn't the best. Yeah, so BFS is iterative. Okay, seems easy enough. This is another problem I did for Amazon. And I know it has something to do with topological sort. Issue is I don't remember how to implement topological sort in code, and also the way we learned it in algos was pretty weird. Like when you get the post order, you like flip it and then like reverse it, traverse. I don't know. It was weird. Do I still? No. Where are my notes? Oh, CS notes. See if I still have topological sort. Loki gonna ask chat. I think some visuals would be nice too. If there's a cycle, no valid ordering exists. Why? Course prerequisites. Course schedule 2. Oh my god, Khan's algorithm. Oh yeah, SECs. Makes sense. Yeah, and then you do DFS again. Who is Kosaraju? Oh yeah. Wait. I'm gonna look something up real quick. Wait, sorry. I was checking something on Twitter. I low-key got carried away. Okay, fuck. Course schedule 2. Alright, guys. I'm locking in, guys. I'm locking in. Um okay. Fuck. A 78. I got a little shriek going on. A little tiny shriek. This is always. I started doing it in the summer. Towards the end of summer, beginning of school. Gave up. Got busy. Winter, decided to try and redo leetcode. Okay, so we had it going on for a bit. Returning to school. Bro. Trying to restart in the summer. Sort of school, restarted. Alright, I'm gonna do it, bro. I'm gonna do it. There's a total of number of courses you have to take. Labeled 0 to num course -1, or num course -1. You're given an array or prerequisites. Okay. Prerequisites of courses. Okay. First, if you want. Whoa, dark mode. Return the ordering of courses you should take to finish all courses. Yeah, okay, yeah, this is definitely a topological sort problem. So you have to take. We have to. The ones that we have to take first. Let's get an example. Oh, I'm so cooked for my interview. Oh my goodness. Oh. Oh, I still have to eat dinner too. Fuck. Oh my god, I have to prep behavioral. Fuck. And homework. Two courses take. To take course 1, you should have to take course 0, 0, 1. Okay. Oh fuck. Let's set this. So this is a graph problem then. This is an adjacency list type problem. And it's direct. It's a DAG. Adjacency list. So key, course, value is going to be prereqs. That's what I'm thinking. Then we're going to topological sort it. Construct the graph and topological sort. Okay. What? So I'm going to say course and prerequisite course PC. For course PC and prerequisites. Let's do default. List. Okay, then hash map. Yeah, so take course when you take. So equals. Oh. Okay, that's constructed the adjacency list. Let's just do a. Let's do a visited set again. So gonna run DFS, I think. Oh fuck. No. No. So there's num courses you have to take. Wait, what 0 num courses? So course. We have to run DFS from the root, no? That's gonna be one that doesn't have any prerequisites. So we're gonna iterate through the values and then try to get the root. So if length of the prerequisite, oh shit. I guess it wouldn't even, there would be nothing there. So if, okay. So we're going to iterate through the number of courses. If I not in hash map dot keys, then root equals fuck. Wait. This is messing me up because there's num courses amount, which is I minus 1. Okay, so for I in range num courses, if I is, okay, yeah. Then root equals I. And then we can run DFS, or define DFS. If, so basically if I in scene, so when is it not valid, right? So if it's already visited, pretty sure that's it, then turn or right? If it's not seen or it's have any prerequisites, right? That means it's a, oh fuck. So right now we have the course to prereqs. I wonder if I should do prereqs to no. Course to prereqs or prereqs to course in the hash map. Because no, because like the key is the prereq. Values are the course is a prereq too. Oh fuck. Which one? Because we need, like, if it reaches the end, right? In our case, we're iterating through the prereqs. Right. We're just gonna keep iterating through the prereqs. If it's not in there, then we reach the end. Fuck. What? I think we have it backwards because we're setting the root equal to that. Let's see. Maybe I can change. Yeah, so maybe I should change. But then I would have to find the sync node and run it from sync node, no? Or So we want to go this way. DFS reverse. No. Then we would start at the source node, which means it does have so we do want to make the root a course that has no prereqs. A course that has no prereqs means or shit. The source node here is so what if I drew it this way? Fuck. Oh, I think I should do that. And then 0. Well, what is the source node in the first case? It means there's no input here, so yeah, so I'm reversing it. Oh, fuck, this is kind of hard. Because it's easy to identify that's the source node in that case, which is if it's not a key. Wait, no, then we have to change it up now. Fuck, right? Because now fuck. Yeah, it makes more sense to do this, like the prereq to courses. How do I find the root, the source node for that then? Like, this is... I don't think that's efficient. I feel like that's not efficient, but that's the only way I can think of right now. And let's see. Now we can run. If I is not seen, and I... That means the sync node. What's the sync node? Then, yeah. then it's gonna not be there. For course in hash map, I'm gonna run DFS. This should okay, so this will append the last one first, and we have to reverse it at the end. Oh, fuck. No, okay. This is definitely... Why? Oh. Should be I, right? Something's going wrong. Oh. For course and hash map I. I think we do want to add I. Please tell me I'm close. That will make me happy. Skip. Yes! You're super close. Oh shit, let's just go code. Why am I lagging?
Hey everyone.
Wait, let me see if I realize what's wrong first. So we set. I think it might be here. I don't know if that's like, I don't know if I'm setting the root correctly. Because then if I, maybe I'm not terminating correctly either. This might be right actually. Because I want one. That is. So prerequisite courses, how do we find the root? We're gonna loop through courses if it's, yeah. If it's not in the values, right? That means no course is a prereq to that. Yeah, so that's right. I think this is wrong. Again, multiple things might be wrong. If I isn't seen versus right. Or how about not it? Or I. Times is not valid, right? How many am I getting? 3. Oh shit, yeah. Okay. Checking I not in. Oh, because it's not gonna look at it. I'm guessing it's gonna get the lists. Like the values are lists. So a singular value is not gonna be within the list. That's fixed. That makes sense. Let's just do this. Oh shit, no. Once per node. Oh shit. This makes sense. This kind of goes with the... yeah, this kind of goes with this. Fix that. Fix that. No cycle detection. Okay, I think the issue... yeah, so you got to do it after every call. That's how DFS works, right? Like the other one. Number of island, we only increment it after a DFS call. Same with this. After a DFS call, then we should append the child, I'm pretty sure. No. No. Okay, wait, I'm lying. I'm lying. Oh. Okay, yeah, because this is after a whole DFS call, then it'll add I, which wouldn't be complete. I give up. I'm gonna watch the video. I swear something looks a little weird.
Welcome back, and let's write some more neat code today. So today let's solve course schedule 2. And if you haven't already seen, I've actually solved the first one, which I recommend watching that video or at least solving that problem before you try to solve this one. It's a little bit more difficult, but it's also very similar. So we are again given n courses labeled from 0 to n-1, and these are basically going to be the nodes in our graph. So this is a graph problem. And again, some courses have prerequisites. So course A has a prerequisite.
So it's just true and false. So this one I should just keep track of the order.
prerequisite of course B. And what that means is you have to take course B before you take course A. So that's pretty intuitive, right? And so instead of knowing if we can take every single course in this problem, we want to know for all of the courses and all of the prerequisites that were given, we want to return the order of courses that we would take in order to finish all the courses. So we care about the order, but there's one little subtlety. It's possible that we can't take all courses given the prerequisites. So if it's not possible, we have to return an empty array. So we have to determine if it's even possible, and then we have to return the order. So this example is pretty simple. We're given two courses, 0 and 1, and the prerequisite is, so in order to take course 1, we have to first take course 0. So then in that case, what's the order? Of course, we have to take 0 first and then course 1. So the output is going to be 0, 1, which is exactly what we have over here. Now, what if I added one more prerequisite? So what if I said, okay, to take course 0, we are required to take course 1 as well. What does that mean? That means, okay, the first prereq tells us that to take course 1, we have to take course 0. And the second one tells us to take course 0, we have to take course 1. Now, look at this. Is it possible to take these courses? It's not. To take course 0, we have to take course 1. To take course 1, we have to take course 0. There's no valid order, so we return an empty array. And we know to return an empty array because we have a cycle in this graph, right? There's a cycle that tells us that's not possible. So now
I do remember it was his answer was low-key different.
But now let's actually look at the general algorithm for it, and it's actually topological sort. This is a standard graph algorithm, but you actually don't even need to know what this algorithm is when you solve this problem. This problem actually teaches you what topological sort is. So similar to course schedule 1, what we're going to do is starting at every single node, we're going to run depth first search on the node. So let's start at node 0. Let's run depth first search on it. To do that, before we do that, we would that tells
I'm just gonna do this problem probably and need to go because I need to go get dinner and also need to do some homework. Yeah.
that's not possible. So now let's actually look at the general algorithm for it, and it's actually topological sort. This is a standard graph algorithm, but you actually don't even need to know what this algorithm is when you solve this problem. This problem actually teaches you what topological sort is. So similar to course schedule 1, what we're going to do is starting at every single node, we're going to run depth first search on the node. So let's start at node 0. Let's run depth first search on it. To do that, before we do that, we would need to build an adjacency list. So for each node, we would need to know its neighbors. So for course 0, we would need its neighbors, which are going to be 1 and 2. Basically, it's prerequisites, right? That's going to be the prereq map. So it's an adjacency list. So I'm just going to quickly write that down. So now we have our prereq map.
Oh, shoot. Sorry, I had to do this. Need to put in my notes real quick, sorry. So run DFS on every island after I recall increment number. Why is time complexity? Oh, then, because we run DFS, visit every Island ones. I mean, yeah. I guess recursive stack. This is recursive stack. And C inset. Okay, now I can get to course go to 2. We go to 10. Oh, yeah.
Map, right? It tells us for each node what are the prerequisites. So 0, right, has 2 prerequisites, 1 and 2, because it has 2 outgoing edges to 1 and 2. 1 has a single prerequisite, 3. 2 has no prerequisites, right? Because look, it has 2 incoming edges, but it does not have any outgoing edges, so it does not have any prerequisites. 3 has a single prerequisite of 2. 4 has a single prerequisite of 0, and 5 also has a single prerequisite of 0. And so we are going to build the output. We're going to do depth first search starting at every single node. And remember, the output we're trying to build is the order in which we can take courses. So just by looking at it, you can tell, okay, 0 has 2 prerequisites, 1 and 2. So of course, we're going to need to take 1 and 2 before we end up taking 0. But let me show you the algorithm. So let's start at 0. We don't update our output yet. We want to take the prerequisites first. So let's go to one of the prerequisites, which we can tell from our prereq map. So we're going to be at node 1 right now. And 1 has a single prerequisite, 3. So we're going to need to take the prereq before we can take course 3. And now we see 3 has a prereq of 2, a single prereq. So all we have to do is take course 2 before we take 3. So now we are at course 2, and lovely that it does not have any prerequisites. What does that mean for us? So far we've taken a path. We've gone from 0 to 1 to 3 all the way to 2, and now we don't have any more prereqs. So we are allowed to take course 2, right? It does not have any prereqs. We can add it to our output. So I'm going to add a 2 to our output. And so what I'm going to do now is cross out 2 because we never have to visit it again, because once we've added 2 to our output, we don't want to add 2 twice, right? There's no need to add a course to our output twice. So I'm going to cross it out so we are never going to visit this node again. And now I'm going to, in our depth first search, I'm going to go back to where we came from. We came from this 3. So now that 3, look, 3 does not have any more prereqs, right? We've already visited 2. It doesn't have any more prereqs. So we can also cross it out. We never have to visit it again, and we add it to our output. And I'm just going to repeat this process all the way along our green path that we just went along. So we're going to go back to 1. 1, we just visited 3. We are never going to visit it, and 1 has no prerequisites anymore, so we can add this to our output. And we go all the way back to 0. Now, hold on a second. So look, 0 has 2 prerequisites, 1, and we already visited 1, but it has one more prereq, 2. So let's go to 2, but we see, right, we already visited it. We don't have to do it again. We can cross this out. So in reality, 0 does not have any prerequisites remaining. So what do? We add 0 to our output. Now, in reality, our algorithm is going to say, okay, we ran depth first search on 0, so now we're going to run depth first search on 1, but we know that we already did that, right? We already recursively did that, so we don't have to do it. And actually, before I forget, since we added 0 to our output, let's cross it out. So we ran depth first search on 0. We're going to try to run depth first search on 1, but we know we already did that. We're going to try to run depth first search on 2, but we know that we already did that. We're going to try to run depth first search on 3, but we know that we already did that. So now we're going to try to run depth first search on 4, which we haven't visited yet. And let's just use our common sense. From just looking at the graph, we can see that, okay, we need to take these courses in this order, 2, 3, 1, 0. What about 4 and 5? Technically, they both have a single prerequisite of 0, right? So once we take 0, we can take 4 and 5, but we can do it in any order, right? We can take 4, 5, or we can take 5, 4. It doesn't matter because these courses aren't a prerequisite of each other. But the way our algorithm is going to work, we are going to start in order. So we're going to go at 4. We're going to see it has a single prerequisite of 0, right? We can see that in our prereq map, and we know we know that we already took course 2, so we can also say, okay, course 4 has also been taken. We've done the prerequisites. We can take course 4. And we're going to do the exact same thing with 5 now. We're going to try to see, okay, it has a single prereq, 0. We've already done that. So now we're allowed to take course 5. So this is the topological sort of this graph, and we know that the topological sort is not necessarily unique, right? Like this could have been a 5 and a 4, so it's not unique. And we also know that if we detect any cycles, we have to return an empty list because that means that a topological sort is not even possible. And by the way, since we are visiting every single node and every single vertex, or rather every single edge, right? We have to travel along every single edge, I think at least twice, and we're probably going to visit every single node up to 2 times. So it is going to be so the time complexity is going to be the number of edges plus the number of vertices, or by vertices, we also mean nodes. So we could also write this as O of P, where P is the number of prerequisites, which is actually the number of edges, and plus N, where N is the number of courses, which is also equal to the number of vertices. And one last thing, how would we actually detect a cycle? Like with our algorithm, well, N is the number of courses. We could also write this as O of P, where P is the number of prerequisites, which is actually the number of edges, and plus N, where N is the number of courses, which is also equal to the number of vertices. And one last thing, how would we actually detect a cycle? Like with our algorithm, well, let's say we had a cycle. So let's say 2 actually did have an outgoing node and it had a node all the way to 0. In that case, what our algorithm would do is, okay, we're starting at 0, we're going to go to 1 just like we did previously, then we're going to go to 3 just like we did previously, then we're going to go to 2 just like we did previously, and then lastly, starting at 2, we're going to go to its only outgoing edge, which is at 0. And at that point, what our algorithm is going to do is it's going to see, okay, we started at 0, we remember that, this is the path that we've taken, we went all the way around and we landed back at 0, so this means we have a cycle, that means we stop our algorithm immediately and return an empty list, we do not have to continue. And the way I'm going to handle this is I'm going to use a hash set, and with that hash set, I'm going to basically remember our current path, so we know we can recognize when we detect a cycle. So now let me actually show you the code. Okay, so now let's write the code, our current path, so we know we can recognize when we detect a cycle. So now let me actually show you the code. Okay, so now let's write the code. The first thing we want to do is build an adjacency list with the prereq. So I'm going to do that prereq, and in some Python, what I'm going to initially do is for every course, I'm going to map it to an empty list. So initially it's going to be a empty list of prerequisites. And now I'm actually going to fill it in. So we're going to iterate through every single course prereq pair. Now what we do is code. The first thing we want to do is build an adjacency list with the prereq. So I'm going to do that prereq, and in some Python, what I'm going to initially do is for every course, I'm going to map it to an empty list. So initially it's going to be a empty list of prerequisites, and now I'm actually going to fill it in. So we're going to iterate through every single course prereq pair in our prerequisites list that we're given. So for this pair in our prerequisites list, I'm going to say prereq of this course. Let's add that to our list. So append it to our list. And this might not have been clear from my picture, but a course has 3 possible states. One, where it's already visited, right? That's where I crossed it out in red. It's already been added to the output. It's been visited. We do not have to ever consider it again. The next state is visiting, right? So it's currently being visited. That's the green path, and that's what's going to allow us to detect if we have a cycle. And the last is unvisited, meaning a course has not been added to the output and it's not currently along the
Sorry.
And now I'm actually going to fill it in. So we're going to iterate through every single course prereq pair in our prerequisites list that we're given. So for this pair in our prerequisites list, I'm going to say prereq of this course. Let's add that to our list. So append it to our list. And this might not have been clear from my picture, but a course has 3 possible states. One, where it's already visited, right? That's where I crossed it out in red. It's already been added to the output. It's been visited. We do not have to ever consider it again. The next state is visiting, right? So it's currently being visited. That's the green path, and that's what's going to allow us to detect if we have a cycle. And the last is unvisited, meaning a course has not been added to the output and it's not currently along the visited path. So that's pretty self-explanatory. So I'm going to obviously create an
Course has been added to output. Okay.
an output list, which is going to be empty. I'm also going to have 2 sets, one visit set and one cycle set. So these sets are going to allow us to know if a node or course has already been visited or if it's currently along the given path, which this is the cycle. not currently along the visited path, so that's pretty self-explanatory. So I'm going to obviously create an output list, which is going to be empty. I'm also going to have two sets, one visit set and one cycle set. So these sets are going to allow us to know if a node or course has already been visited or if it's currently along the given path, which the cycle is obviously going to let us know, is going to help us detect cycles. Now I'm going to define our depth first search function. As you can see, I'm doing it inside of another function, basically so I don't have to pass all these parameters into this, and all of these variables will be accessible inside this function. So the only thing I have to pass in is the course number that we're currently visiting. So the first thing I want to do is detect a cycle. So if this course is already inside of our cycle set, that means we're visiting it twice. That means we've detected a cycle. That means we're going to return false, and then that we're currently visiting. So the first thing I want to do is detect a cycle. So if this course is already inside of our cycle set, that means we're visiting it twice. That means we've detected a cycle. That means we're going to return false, and then we're going to be able to terminate our algorithm and return an empty list. If a course has already been visited, that basically means we don't need to visit it twice. So I'm going to return true. We're not going to stop our algorithm and return an empty list, but we don't need to visit this course twice. Now I'm going to recursively run depth first search, but before we do that, we do have to add this course to our cycle. We want to be able to know if we have a cycle. So if we ever see this course again, recursively, we'll know that been visited. We're going to return true. We're not going to stop our algorithm and return an empty list, but we don't need to visit this course twice. Now I'm going to recursively run depth first search, but before we do that, we do have to add this course to our cycle. We want to be able to know if we have a cycle. So if we ever see this course again, recursively, we'll know that we detected a cycle. But for now, we're going to go through every prerequisite of this course. So from our prerequisite map, we're going to get all of the prerequisites. We're going to run recursively depth first search on this prerequisite. And if that returns false, because we know we have two return values, true and false, if it returns false, we know we just detected a cycle. So in that case, if this equals false, we have to also return false. If it doesn't equal false, it equals true, then we're just going to continue to go through all the prerequisites and continue to run depth first search. And when all of that is said and done, we will take from our cycle, we're going to remove the course because it's no longer, we will take depth first search. And when all of that is said and done, we will take from our cycle, we're going to remove the course because it's no longer along the path that we're going, so we can remove it from cycle. We can also add it to visit because we just went through this course and we went through all of its prerequisites. Therefore, we can say that it's been visited. And since this course has been visited, we can finally add it to our output, which was our ultimate goal. So we can add it to our output because we just went through all of its prerequisites, and from those prerequisites, we just added them to our output. So now we are allowed to add this course to our output. We can only add a course after we've added its prerequisites, right? And since we added this to our output, we know it's a course we're allowed to take.
So I guess in this case, I didn't ask chat, but I'm wondering if we've already seen it, why don't we, like, how is that a valid state if we've already seen it?
So we can return true, not false. We're going to return true. Everything was this course to our output. We can,
because usually if we run DFS and we've already seen a node, right? Oh, then we just don't run it again on that.
only add a course after we've added its prerequisites. That's right. And since we added this to our output, we know it's a course we're allowed to take, so we can return true, not false. We're going to return true, everything was fine. Because since we're returning true, we know that this never executed, so we never had to return false.
Oh, because even we visited,
we ultimately
like multiple course can have the same prerequisite, so
returned true. So now
course has not. Okay, course has been output.
we've basically written all the code that we need. We just have to execute it. So we have to go through every order, but you technically on every single course. But we do have to check if the return value of any of these calls happens to be false. What that means is we detected a cycle. And what that means is we are forced to return an empty list. We're not going to return output. We're going to return an empty list because it's impossible to take the given courses. Detected a cycle running. And when that happens, we will be in. So you can see I'm going to see the entire code on one page. So this is the entire code. I'm going to run it and show you that it is pretty efficient. Okay, whoops, one little bug. Output is a list, so the function to add, hopefully I don't have any other typos. And yes, you can see that this is
a little tricky, TBH, IMO. Okay, let's try to code it. From what I remember, wow, this video is about to reach 2 hours. 2 hours for 2 problems, bro, and the first one isn't even that bad. For like, this is course schedule. I'm trying to do course schedule 2. Okay, let's build the adjacency list. Okay. Wow, that's a good amount of code. I guess not actually. Okay. Okay. Actually, I do like those comments. Fuck. It should just be output, yeah. So we initiated the adjacency list. The scene and cycle. Find DFS for I, which states. Because we have a cycle. going to terminate, return true. How come that number of islands though we wanted to, or we were able to see? Okay. So then we add it to the cycle. So for each of these prereqs, we run BFS on these. When do we append to res? Shit, there's a lot I'm missing. Oh yeah. Is this valid? I think this means none. Okay, whatever. So if it returns false, return false. This has to come after. Yeah. shit. Bro.
You can see that
What? Huh? Bro, what the hell? So what I messed up, I forgot about this part. Bro, what the hell? Boy, what the heck? Okay. Let's write out notes. So the course and the prereqs, scene set, cycle set. Okay. Also, we call it DFS, so if it's already been seen, then return false. If it's unseen, don't need to process it further. I feel like this is, can we not just say DFS PC? Should it return? Fuck. Should it not return? What? Yo, I did not know it did that. Oh shit. Okay, like shouldn't it return false eventually? shit. Why do we, okay, so why do we need the commented part instead of just being able to? Because if this is false, because if this is false, so if I cycles return false, 19, you can just go ahead, add Ivan. Okay. Kind of get it, but not really. Let's still ask and make sure. Deep inside one, and it caused Imagine it one at one. Okay, that makes sense. So if any of those recycles, then this fails. Okay, yeah. Fuck. Okay. Okay, makes sense. So time complexity, I'm gonna guess this is oh, he already said it's, I mean, it would be O of V plus E, which is O of this E, where V equals courses, E equals prereqs. But there are more courses than prereqs, so it should simplify to not necessarily. Space complexity would be O of V plus ES. What would it be? V plus U as well, right? Yeah. Because the hash map. Oh, I was thinking, wouldn't this just be O of V? V? No, because the list. Because the list is prereqs, which is E. I'm actually going to ask about this. So it is V plus E, because adjacency list is V plus E, as I thought. Visitor sets can hold all courses, which is V result list, V recursive stack, goes as much as the courses. Sets. Let's see. Okay. Makes sense, makes sense. Probably just gonna try to do course schedule 1 on my own after this. But yeah, that's it for today. See y'all.